the next session of today for paper presentation. This session focuses on fault attacks, and for this session we have two of our chairs, session chairs, Dr. Shantanu Sharkar and Dr. Mohit Gupta. During the session, when the paper will be presented, after that you can post your question on the Q&A platform, and after the session of when the break will be there, you can join to the authors directly with the Google Meet link shared in the event platform. So over to you, to the session chair. Thank you.
Yeah, can we start now? Yeah, so good afternoon, everybody. First talk is on differential fault attack on Espresso. Authors are Bhagavan Vathe, Siddharth Tiwari, Ravi Anand, Dibyendu Roy, and Shubhay Maitra. Ravi Anand will be speaker. Ravi, please start.
Thank you, sir. Good afternoon, all. I'm Ravi Anand, and I'll be presenting our work Differential Fault Attack on Espresso, which is a joint work with Bhagavan Bhate, Siddharth Tiwari, Dibyendu Roy, and Shubhomoy Mitra. Espresso is a 5G standard cipher which is based on 256-bit NFSR and has a non-linear filter function of degree 6. It has 14 non-linear feedback functions. The key size of Espresso is 128 bits and has a initialization vector size of 96 bits. Espresso has an initialization round of 256 in which the key stream bits are not outputted. So our work is a differential fault attack on Espresso. So differential fault attack can be considered as a special case of differential attacks. In this case, in this model of attack, the differential fault attack, the adversary becomes more powerful than the adversary of a differential attack. In the fault attacks, the adversary is allowed to introduce a difference in the state bits or the initial states of this key stream generation phase of the cipher by injecting faults into the state after the key scheduling phase. And this difference, which is introduced in the initial state of the key stream generation phase, makes a distinguishable impact on the key stream bits. And then these the information you got from here is used to either obtain the values of the initial state or the key. There are a few assumptions that we have made in this model of attack. The first is that the adversary has the required tools for injecting the fault. Also, adversary can inject multiple faults at that exact timings that we require or the exact round at which we need. The adversary can also restart the cipher multiple times with the same key and IV. And adversary can introduce controlled number of faults. We also assume that the adversary has no knowledge of the location at which the fault has been introduced, and so we need to first locate where the faults were introduced in the initial state. So let us consider that a fault has been injected in some unknown location, say F of the state of the cipher, and the adversary has access to lambda key stream bits for every fault injected into the cipher. Then the entire process of identifying this fault can be divided into two parts, the offline phase and the online phase. In the offline phase, first of all, the adversary computes a signature, which is a vector of length lambda, which is the lambda key stream bits that we require, and corresponding to a known fault location, say F here. SF is this vector where each SIF is computed as half minus probability of ZI not equal to ZIF, where ZI is the key stream, fault-free key stream, and ZIF is the faulty key stream. That is when the fault has been injected at a known location F. As we can see from the formula above of SIF, that it will always be between minus 0.5 to 0.5, and the signature is considered to be very strong if this value, the sigma SF is close to 1. The closer it is to 1, the easier it is to locate where the fault has been injected. Now, when in the offline phase, the adversary uses the assumption of resetting the cipher to its original state, in which the cipher is rekeyed using the same key and the IV. and then the adversary injects a fault in some unknown location, say gamma, and will record the corresponding key stream Z0 gamma, Z1 gamma to Z lambda minus 1 gamma, where this is known as the faulty key stream. Now we need this W many times key stream, such faulty key streams, because W has to be large enough so that we have enough equations and to solve to solve and then derive the state of that cipher. So we repeat this process W many times, and then we have an access to W plus 1 key stream sequences, where W are faulty key stream sequences and 1 is that fault free sequence that we have. And then the adversary will compute a trail vector for each unknown fault location lambda, where it is defined as this, that d lambda is equal to half if it is equal, and it is minus half it is not if it is not equal, for all I from 0 to lambda minus 1. Now by intuition we can say that if SF matches with the trail, if the signature at certain fault matches with a trail of certain unknown location y, then that F lambda should ideally would be the correct fault location. But to find this, generally it has been assumed sometimes that this does not happen, and there are we have to check for more times, and for that we use a Pearson's correlation coefficient, mu SF mu, and we compute this for each fault location. So for each lambda, which is for each gamma, the adversary will calculate this correlation between the trail at F, which we knew, and the trail that of the unknown location fault injected at unknown for each possible fault location F, and then the adversary will create a list of fault indices, say L gamma, sorted with the reducing correlation coefficient. That is, with the value with the highest correlation coefficient will be the topmost, and with the lowest will be the bottom. So we'll make these many tables or lists, as we say, and we have to construct W such lists because we have so many for faulty key stream. Now once that is done, the adversary will consider a set of possible fault locations, PG row 0, row 1 to row W minus 1, where each row I is the first is the first list from Li. So row I, so say row 0 is the first element of the list L0, row 1 is the first element of the list L1. In this way we take all those the first elements or the elements with the maximum correlation from each list, and then we try to solve this system of equation involving the state bits. After solving the equations and recovering the state, the adversary finds a 2n length key stream from the state, and then it will check it with the available key stream. If it is a miss, then the adversary will repeat the solving the equations with the next best set of locations. Now for Espresso, so this was the method in which the fault the location of the fault can be found. So in case of Espresso, we found that this figure gives the signature of this Espresso, and for we can see from this table, from this plotting, that the signatures for Espresso are very good, which means that we have a very high chance of locating the fault locations easily. This shows the correlation between the trail and a signature. And as you can see here, we can see that the maximum correlation between a certain F and a certain unknown G is completely equal to the correlation between the signature at that point of that signature and the trail of exactly that fault location. This means that it was very easy to locate faults injected in Espresso. Now, what happens in the online phase we try to find out the state bits of Espresso, so Espresso exactly has 14 nonlinear feedback bits. Now these feedback bits will actually make the key stream bits more complicated as the rounds increases. So to tackle this, what we do is we introduce new variables in each clocking for all these 14 feedback bits. And so if you are using n key stream bits for our fault model attack, then the total number of new variables will be 14 into n. And so the total number of variables that we have will be 14n plus 256. This complete process is described in algorithm 3 of our paper. Now in the online phase, we inject some random faults in the cipher, and we generate a faulty key stream bits as we have explained it before. Now these faults are actually injected just after the key scheduling phase of the cipher, and then the equations are formed using the state differences for fault affected state. Now as we have explained it, as I've explained it even before, that now if a fault is injected at say at a location F in the state, then this difference del xi will be 0 for all xi if they are equal, and if they are equal, but except at this fault location the difference will be 1. So we make equations relating to this, but before going that we need to generate certain equations for all these difference of XOR, AND of 2 bits, AND of 3 bits, up to AND of 6 bits, because there is a monomial of 6 bits, the 6 of degree 6, nonlinear monomial of degree 6. So we compute this difference expression for all higher order terms up to 6 terms, and then we compute the expressions of difference feedback bits, and using the techniques that we have already explained before, which is explained in more detail in algorithm 4 of our paper, we form this differential key stream bit equations. Using this key stream bit equations, we then try to solve and derive the secret key. So our experimentation, we considered fault locations. We injected 4 fault at locations 212, 33, 155, and 3 out of the state bits which starts from 0 to 255, and these are selected randomly. This is one of those fault locations which we are seeing here, and we have 200 key stream bits which took it. And the above mentioned techniques were used to derive our system of equations. Now once the system of equations were generated, we fed this to the SAT solver, and in 400 seconds it returned the correct set. Then by reversing our key IV initialization process, we were able to recover this secret key. Now this whole experiment was done in a normal laptop, which is a 8 GB RAM, 8 GB Ubuntu. And to check the correctness of our work, we also performed a simulation in the hardware, and we found that the work that we had, the values that we obtained were correct. So in conclusion, we can say that Espresso is not completely secure against differential fault attack if all those assumptions are taken care of, and also we only required four faults into the state of the cipher after the key scheduling algorithm, and we were able to obtain the secret key in a practical time. Thank you.
Thank you, Ravi. Any
you.
question?
Ravi, am I audible?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
So now that you know what are the faults in this algorithm, can you
Yes, sir.
can you improve this?
Sir, one thing that that is general, which we see generally in fault attacks, as I had said before, the initial state, once we find, we can reverse it and find the key and the IV that were used. So one of the options could have been that the key scheduling algorithm could have used key bits to make it, that reverse would not be possible. So that could be one thing, that obtaining state bits will not lead to obtaining the key bits. That could be one thing. The second thing is maybe. So this was one thing that I said.
No, no,
Others will have to.
I think basically you have attacked that key scheduling algorithm, not the real algorithm, right?
Yes, sir. Yes, sir.
Yeah,
Yes,
yeah.
sir.
So I think okay, fine.
Yes. So for that is.
So is there any other question from the audience? Is there any question? Okay, so over to you, Professor Santanu.
Yeah. So how many faults are required, Ruby? Maybe I missed that
For
part.
this, sir, we required 4.
Four
Minimum
faults
was
only.
4.
Oh, only
Yes,
four.
sir.
Okay, very good. Okay, I don't have any
Thank you.
other questions. So any. Otherwise, we can thank Ruby.
Thank you, sir.
Okay, then we can move to the next speaker.
Hi, hello, can you hear me?
Yeah.
Yes, I will try to see I can share my screen. I moved to the web browser, so yes. Do you see my
Yeah.
presentation?
Yeah.
It works.
Very good. Okay, so let me then introduce you. So our next speaker is Andy Russon, and title of the paper is Differential Fault Attack on Montgomery Ladder and in the presence of scalar randomization. Andy, please proceed.
Okay, hello everyone. So, yeah, so my name is Andy. I just finished my PhD at the University of Rennes in France and the French company Orange. And I will present my paper Differential Fault Attack on Montgomery Ladder in the presence of scalar randomization. So first, a little bit of an introduction on elliptic curves and differential fault attack. An elliptic curve is defined with a Weierstrass equation and would look like this figure on the overall prime field. And starting from a base point P and using the group operation on elliptic curves, so point addition, we can compute the scalar multiplication by an integer k. So by a sequence of point addition, we can compute k times p equals q efficiently. And what happens is that if an attacker is able to make a fault in the middle of the execution, eventually we'll get an erroneous output q prime. And the idea of differential fault attack is to exploit the difference that was made on the erroneous output q prime compared to the point q. For example, if we make the difference, which could be only depends on a few bits of the secret scalar k. And one context in which this is very useful is the signature scheme ECDSA, because signature generation always involves a secret scalar k, which is called a nonce. And one key feature of this signature algorithm is that the verification mechanism of ECDSA allows us to recover both the correct point q and the erroneous point q prime from the faulty signature. So it is very useful for a differential fault attack. And then if we are able to apply the attack and recover a small part of the secret nonce k, then it is vulnerable to lattice attack. So I won't expand onto this part of the lattice attack. It is explained in the paper and in many other papers. But what we just need to know that once we have removed the part that we know on the scalar k, then if the remaining part is small enough, then we can translate all of the signatures that are collected into a shortest vector problem, which can be solved with lattice. Okay, so the first part, I will present a new proposition of a differential fault attack on a specific scalar multiplication algorithm, Montgomery ladder. So this algorithm takes as input the R scalar k and a base point p, and it works like this. So there is a point R0 and a point R1. The point R0 is initialized with the point P, and R1 has 2 times P, so the point P added with itself. And on each step of the algorithm, there is always a point addition and a point doubling. So when the scalar bit is 0, the result of the point addition is stored in the point R1, and the point doubling is made on the point R0. And when instead the scalar bit to be processed is 1, then the result of the point addition is stored on the point R0, and the result and the point doubling is made on the point R1, and so on until the end of the scalar multiplication. And then the point that is in R0 at the end is the output that we are looking for, k times p. To summarize how the algorithm works, we need to really retain as information those two things. There is a loop invariant, and if we look closely at each step, the difference between the point R0 and the point R1 is always the point P. And using this, we can rewrite what happens at each step. In fact, what happens is that the point R0 is replaced by 2 times R0 plus the new bit times the value of the invariant. And this is what happens if, of course, everything occurs correctly. And using that, it becomes easier to explain what happens if an attacker disrupts this execution. So our idea of a fault attack is to suppose that an attacker is able to invert the point R0 and R1 somewhere in the middle of the execution of the algorithm. So what happens is that the difference of the point R0 and R1 will not be the point P anymore, but the point minus P. So starting from this moment on the execution, the scalar multiplication will use this new invariant. So the next, when we are going to process the next bit, the point R0 is multiplied by 2, then we add the new bit times the new invariant, and so on with the next bit, until all the least significant bits are processed. So now it is easy to, with this description, to see the expression of the point Q prime. So I have represented with K, we had the most significant bits that were processed before the fault, and K with a bar for the least significant bits that were processed after the fault. So now what happens is that if we make the difference of the point Q and Q prime, we see that the most significant bits are cancelled. So we get a point that only depends on the least significant bits. And alternatively, we can make the sum, which will depend on the most significant bits. So it depends for whichever case is appropriate. So if the fault occurs near the end of the scalar multiplication, then we compute the difference, and we are looking for the least significant bits, maybe by an exhaustive search, or maybe by running a discrete logarithm to search the value in a smaller range. And there are a few details interesting for this attack in that we have seen that the fault only inverts the point R0 and R1. So it does not impact the point additions in the scalar multiplication. So those operations are still valid elliptic curve operations. So the point R0 and R1 will still satisfy the curve equation. However, since we have a change, so since the invariant has changed from P to minus P, then if we check the consistency of this value, we can detect the fault. Well, that's true except for specific formulas. Let's take a look at the X-only formulas. Those formulas only use the X coordinate of the point R0 and R1 in the point addition formulas. So we cannot distinguish the point R0 from the point minus R0 because those points have the same X coordinate. So the difference R0 minus R1 and R1 minus R0 cannot be distinguished from each other. Basically, the point P cannot be distinguished from the point minus P. And that is true even if we try to reconstruct the missing coordinate Y, because it will yield the correct invariant. Well, to explain a little bit about this part is because that the recovery formula will use the point P, the input, which is the expected invariant. But the current invariant is minus P, so it will introduce a minus sign, which will autocorrect itself with the minus sign of the new invariant. So basically, which will construct P as minus P. And this properties is also true for the cosette formulas. So those formulas uses projective Jacobian coordinates such that the point R0 and R1 share the same Z coordinate, and this coordinate is not used in the computation. So those are pretty efficient. And when they use a recovery for the Z coordinate at the end because it is needed to get the affine output, then we have the same thing that will happen. It could yield the correct invariant. To finish this first part, I still need to address the issue of the realization of this fault. In practice, there is a conditional swap to avoid bound condition in cryptographic libraries, because it is important that the cryptographic code does not have bound conditions. It uses a Boolean variable, which is called p-bit, which stands for previous bit, and keeps track of the current state of the point R0 and R1. What happens is that the point R0 and R1 will be swapped so that the point additions and the point doubling occurs with the correct values. So when p-bit is 0, it just means that the points are in the normal set, and p-bit is 1, it just means they are inverted. And we can rewrite the formula for invariance, such as the formula that you can see. So the idea is that under the skip instruction fault model, if we skip the instruction that update the Boolean variable p-bit with the new bit of the scalar, then since it's XOR operation and the new bit of the scalar is 1, it just means that the Boolean variable will not be updated. And this will have an impact on the current state of the point R0 and R1. It just means that it will not be consistent anymore. So basically, if we compute the difference, we try to compute the formula for invariant, it will be minus p, and which is exactly the desired effect for our attack. There are some other possibilities, for example, by targeting the lag 8, which will store the current bit of the scalar to be used for the next step of the algorithm. So it will produce the same effect, but starting from the next iteration. And there are also other possibilities that we're using other fault models. Some can target directly the conditional swap, but it depends on the method that is used for this conditional swap. There is one example that is given in the paper where a random fault in a register, in the register p-bit, which can produce exactly the effect that the desired effect. So now the second part, I will talk about differential fault attack in the context of a scalar randomization. So it is for differential attack in general, but we can suppose that the differential fault attack is exactly the attack that I just presented. I will expand on the case of the Euclidean splitting. So the scalar is randomized with an Euclidean division using a random integer m. So then scalar k is split in 3 parts with the quotient, the random divisor, and the remainder, and everything is put back together in the end with the final point addition. So there are 3 individual scalar multiplication. And it's still possible to recover some very useful information for a lattice attack, eventually when the scalar k is a private key. The idea is to attack the scalar multiplication with the random divisor. So suppose it is our attack as I just presented earlier. So if we make the difference between q and q prime, we'll get a point that depends on the least significant bits of the value m. But this time, it's not the point p that we have at the end, it's the point r, which depends on the quotient, which is unknown to the attacker, and might be quite big, so it's not possible to recover it. Well, it's still possible to do something. There is some strategy that we can devise to recover both the random divisor m and the remainder b. First is to guess the difference that was made on the scalar multiplication with the random integer m. So basically, we can, in our attack, use the least significant bits of m. When we have done that, we can compute a candidate for the point r. And then we can apply the baby step giant step strategy. So this algorithm, it is composed of 2 parts. The first one where you compute all the possible values for b times p, which can be pre-computed because the point p is the base point. And on another side, we can compute the list of possible values for q minus m times r. So in our attack, since we already have the least significant bits of m, then we can just make an exhaustive search on the most significant bits of m. And when there is a collision, then it will produce a candidate for m and b. So overall, the cost depends on the size of the randomizer because we will need to run an exhaustive search on this value. So let's suppose that lambda is 32 bits, then it's something that can be still tractable to realize the attack. So it is very useful for lattice attack with for lattice attacks in ACES, because then the only part that is unknown is the quotient. And we can still use, in the case of K is a fixed private key, then we can use the Chinese remainder theorem by attacking over scalar multiplication. I'm not sure I will have too much time to address the over randomization method, but it is explained in the paper. So we can still attack the blinding with the group order, which is a classical countermeasures, which is the second countermeasures by Coron. So the scalar randomized by K plus a multiple of the base point order. It's possible if to apply. It's possible to use a differential fault attack as long as the number of bits that is revealed by the differential fault attack is larger than the randomizer. And there are also multiplicative splitting, which is a little bit complicated, a little bit more complicated. But in both cases, the cost depends on half the size of the random divisor. Yes, the randomizer. More detail in the paper about that. So just let's conclude. So I presented a new differential fault attack on the Montgomery ladder algorithm for scalar multiplication on elliptic curves, which can bypass some classic countermeasures. Well, not still possible to apply some countermeasures. I addressed that in the paper, but some classic ones such as point validation and invariant consistency check can be bypassed under some circumstances. And I presented also evidence that some scalar minimization method can still be vulnerable to differential fault attack. And finally, there are some simulations that are available on the GitHub repository, just to which address which present well, you can still take a look at it. Thank you very much.
Yeah, thank you, Andy. Any?
So is there any question from the audience? Is there any question? So no question. So over to you, Professor Santanu.
Maybe we can move to next speaker. I think some network issue.
Hello. I'll just share my screen. That doesn't seem to work. Or can you see it?
Yeah, I can see you.
Perfect.
Yeah. Yeah, so let me introduce you.
If you can just stop screen share, please, for 2 minutes till the introduction. Thank you.
Yeah. So our last talk on this session is by Julius Hermelink, and author of the papers are Julius Hermelink, Peter Pessel, and Thomas Poppelman. Title of the paper is Fault-Enabled Chosen Ciphertext Attacks on Kyber. Julius, please proceed.
Thank you for the introduction. And yes, as mentioned before, the title is Fault-Enabled Chosen Ciphertext Attacks on Kyber. And this is joint work with Peter Pessel and Thomas Pöppelmann. As the title suggests, we present an attack on Kyber using the combination of a chosen ciphertext attack and a single bit fault attack. Kyber is a CCA2 secure post-quantum key exchange mechanism that is a finalist in a NIST standardization process and is based on the hardness of the MLWE problem. It defines 3 parameter sets. And what will be important here is that it's built from a public key encryption scheme using a variant of the FO transform. We'll be working over FQX mod x to the n minus 1. So as I said, it's built from a public key encryption that defines encrypt and decrypt function, and then the decapsulation of the key exchange mechanism works as follows. An incoming ciphertext C is decrypted to obtain the message M that was encrypted in C. And this message M is then re-encrypted using the same randomness that was originally used to encrypt it. The resulting ciphertext of the re-encryption is then compared against the submitted ciphertext, and in case that they are equal, a shared secret is outputted, otherwise the decapsulation fails. During this decryption step, the message has to be recovered from a noisy version of the message. The message here is a polynomial. I'll explain how bits are mapped to coefficients in the next slide. And onto this polynomial, there is a noise polynomial added. All coefficients of this noise polynomial are small noise. And what is important is that this noise polynomial contains secrets E and S. So either E or S give the secret key. All other terms are known to the attacker. So during encryption, 0 bits of a message were mapped to a 0 coefficient. Each bit gives a coefficient, and 1 bits were mapped to Q divided by 2. Now, during the decryption step we saw on the last slide, and that happens during the decapsulation step, this message has to be recovered from a noisy version of this polynomial. And this is done by mapping a coefficient to a 0 bit if it is closer to 0 than to Q divided by 2, and otherwise to a 1 bit. We can visualize this on a circle with the numbers from 0 to Q minus 1 mapped onto a circle. And the red points here would be the message bit with bits without any noise, message coefficients, 0 and Q divided by 2, and then noise rotates us either counterclockwise if it's negative, or clockwise if it's positive. So this gray point here would be an example of a coefficient that was originally a 0 bit and then had some negative noise added to it. And then the upper half of the circle is mapped to 0 and the lower half is mapped to 1. And of course, if the noise is small, then this gives the original bit. We can use this to construct error attacks. So if we add Q divided by 4 to one coefficient of this noisy message polynomial, then this is a quarter rotation on the circle. And this might cause an error, and this causes an error exactly when the noise is positive. Because if the noise is negative, then we rotate it counterclockwise, and then a clockwise rotation will not take us to the other half of the circle. But if we were here, for example, then this would cause a decryption error. So what happens if we add q divided by 4 and then observe decryption errors? We know if this noise polynomial containing the secrets E and S is positive or negative. That means adding q divided by 4 and then observing decryption errors gives inequalities, inviting the secret. Now, decryption errors are not necessarily, or decapsulation errors are not necessarily decryption errors. If we submit a manipulated ciphertext, then of course this will fail because of the FO transform. Otherwise, we wouldn't be CCA2 secure. A recent fault attack by Pestle and Prokop takes advantage of these decryption errors. They fault the decoder to cause the addition of q divided by 4. And then from each decapsulation that is faulted, they recover exactly one inequality, as described before. They then use the knowledge of the distributions, the secret coefficients that are sampled from a known distribution, and update them successively using the inequalities, and this then converges if enough inequalities were retrieved. This is a powerful attack, but it has some limitations. It is prevented by shuffling the decoder. It has a very specific fault model and is therefore highly dependent on the implementation. So what we do is a bit differently. Instead of sending in a valid ciphertext, which we then fault, we first sample a valid ciphertext C and then add q divided by 4 to one coefficient. And this ciphertext C prime with this q divided by 4 error already in one coefficient is submitted to the device under attack. That means that the device never sees the valid ciphertext, but gets the manipulated ciphertext in the first place. So C prime is submitted to the device, decrypted by the device. Sorry. A message M prime is retrieved from this manipulated ciphertext and then re-encrypted by the device. While this happens, we introduce a fault, a single bit fault, that changes C prime back to C. So the device now has this re-encrypted ciphertext C prime prime, but compares against the original ciphertext C and not against the manipulated ciphertext C prime. What happens is that the device decrypts C prime, which is C with a q divided by 4 error added in one coefficient, but the result of the re-encryption here is then compared against the original ciphertext and not the manipulated ciphertext. And what we achieve by this, we have two cases. In case that the addition of q divided by 4 causes a decryption error, C prime causes a decryption error, here we get a different message here that is not the original M that was used to create C. And then, of course, the re-encryption also gives a different ciphertext, which differs from C. So we will see a decapsulation error here. If C prime causes no decryption error, then in decrypt, we get the same message M prime is M. And then the re-encryption also gives the same ciphertext, and C prime prime is C. So we do not see a decapsulation error. So now by observing decapsulation errors, we can actually observe decryption errors. And as we saw before, that gives inequalities. So each failed decapsulation gives an inequality, and each successful decapsulation also. So what does our fault have to do? It needs to correct either C prime or the result of the re-encryption so that this comparison works. That means it needs to be applied after decrypt was called and before the re-encryption comparison. and it needs to target either the stored ciphertext or the ciphertext obtained from re-encryption. And the fault model is to either set, reset, or flip a single bit. That it is a single bit is because of how compression and Kyber works, and that we can either set, reset, or flip is because we can control the input. We can choose if we want to set, reset, or if we don't care if we reset or set a bit. We also present a new method of solving such inequalities, those inequalities we then obtained, and we use belief propagation to do this. Using belief propagation, we improve the previous method by using less faults and requiring much less memory. This belief propagation works by, for each unknown coefficient of the secret, initializing a variable node. And each inequality gives a check node, and these check nodes then update the distributions coming from the variable nodes. So summarizing, what is our approach? Instead of sending a valid ciphertext and then applying a fault to cause this Q divided by 4, we send a manipulated ciphertext that already has this error and then use a fault to correct. Why is this better? Or why do we believe this to be better? The manipulation is performed offline. The error is already contained in the ciphertext that is submitted. Therefore, whenever we observe a successful decapsulation, that means that the fault worked. Otherwise, the decapsulation cannot work. That means if the fault is really unreliable, we can still work with it. There's absolutely no problem. We can just need more of them. The fault is also not prevented by shuffling the decoder and several other very specific countermeasures, because it may be introduced over a very long time span and at several places. And therefore, it's also less implementation specific. How many faults do we need? Here on the left side, we see the success rate and the number of inequalities. Remember, one inequality corresponds to one fault, corresponds to one decapsulation. And depending on the version, for Kyber 5.12, to be certain to be able to recover the secret key, we need 6,000 faults. For Kyber 7.6.8, we need about 7,000 faults. And for Kyber 10.24, we need about 8,500 faults. The recovery method is pretty efficient. We tested this on Intel Xeon Gold, 32 and 8 threads, and here we stay well below an hour for all our experiments. And it can actually be run on a normal laptop. There's no special hardware needed for the recovery method. Thank you for listening.
Thank you, Julius.
Is there any question from audience? Is there any question? Okay, so over to you, Professor Shantanu.
I don't have any question. Let me see in chat box. No, nothing is here. Oh, thank you, Julius. Then let us thank him.
Thank you.
So thank you, everyone. Thank you for presenting so nicely. And thank you, Professor Shantanu and Dr. Mohit, for joining. So the next, now we'll be having a small tea break, and the next session will begin at 6:30 sharp. And we'll be there right back. Thank you.
Thank you. Bye.